Hello, and welcome to our 2023 review. 2023 turned out to be a pretty good year, with amazing results from not only Hubble, but from the James Webb Space Telescope as well, and some other sources. We'll start with an update on DART. That was the collision of the asteroid that they're trying to turn into a way to make sure that asteroids never do us in. Staying in the solar system, we'll also cover the Parker Solar Probe. It's been orbiting the Sun for some time now, and in 2023, it made its closest approach to the Sun, moving into the Sun's corona. That's quite a feat. Moving beyond the solar system, we'll see a number of molecular clouds, a brown dwarf, a star that's fusing helium, some Herbig-Haro objects, and we'll examine the possibility of an intermediate mass black hole in the M4 star cluster. We'll take a deep dive into the Crab Nebula and Cassiopeia A. We'll do a little astrochemistry in the Iris Nebula, and we'll take one last look at Fomalhaut and the disappearing planet that we used to talk about. Moving beyond the galaxy, we'll cover some dwarf galaxies, a runaway black hole, intergalactic stars, two merging spiral galaxies. We'll see how to calculate the mass of a black hole by the distortions it creates via gravitational lensing on galaxies much further away. And we'll take a look at three galaxies that we see through the El Gordo galaxy cluster. We'll see a very early proto-galaxy cluster, one of the first galaxy clusters ever found. And we'll see some of the oldest galaxies ever discovered. We'll end with a few images from the world's newest space telescope, Euclid. I expect we'll see more from Euclid in 2024. I trust you'll find it interesting and informative. Thanks for watching.
Detailed follow-up observations on the Didymos-Dimorphos system measured the Dimorphos orbit around Didymos at once every 11 hours and 22 minutes. That's a full 33 minutes shorter than its orbital period before the collision. This dramatic increase turns out to be caused by the production of at least 1 million kilograms of material ejected by the impact. That's just over 1,000 U.S. tons. In addition, Hubble has detected 37 boulders knocked off the asteroid by the force of the collision. The total mass of these boulders is about 0.1% of the mass of Dimorphos. They are drifting away from the asteroid at around 1 kilometer per hour. That's 0.62 miles per hour. In 2024, the European Space Agency's Hera mission plans to launch a spacecraft to the system. It will perform a detailed post-impact survey that will turn the DART experiment into a well-understood and repeatable planetary defense technique that might one day be used for real. We'll see more on this in the 2024 review. In 2023, the Parker Solar Probe set a new speed record and entered the Sun's atmosphere, the corona, for the second time.
25 seconds.
The probe, launched in 2018, has an elliptical orbit around the Sun that brings it closer on every pass. In 2022, following a gravity assist from a Venus flyby, it reached 586,000 kilometers per hour. That's 364,000 miles per hour. It passed within 8,500,000 kilometers of the Sun's surface. That's 5,300,000 miles. That's inside the Sun's corona. The 2023 pass was faster and took it even closer. The Sun has a superheated atmosphere, made of solar material bound to the Sun by gravity and magnetic forces. As rising heat and pressure push that material away from the Sun, it reaches a point where gravity and magnetic fields are too weak to contain it. At that point, known as the Alfvén critical surface, the solar atmosphere ends and the solar wind begins. Solar material, with the energy to make it across that boundary, drags the sun's magnetic field with it as it travels across the solar system, to the Earth and beyond. During its 8th flyby, at around 13 million kilometers, or 8.1 million miles above the solar surface, the Parker Solar Probe encountered the sun's atmosphere magnetic and particle conditions. It had crossed the Alfvén critical surface and entered the solar atmosphere. This is quite an accomplishment. The probe will provide us with deeper insights into our sun's evolution and its impacts on our solar system, including the solar wind and its impact on the Earth. This image by the James Webb Space Telescope's near-infrared camera features the central region of the Chameleon-1 dark molecular cloud, 630 light-years away. The wispy blue cloud material in the center is illuminated in the infrared by the orange glow of the young protostar SED 110 IRS-4 in the upper left. The light from numerous background stars, seen as orange dots behind the cloud, is used to detect molecules in ices in the cloud. The 2 background stars used in this study are circled. The molecules in the ices absorb the starlight passing through them. This creates a dip in the light that reaches us for each element in the ice. In addition, an international team of astronomers were able to identify frozen forms of a wide range of complex organic molecules, such as ammonia, methane, and methanol. These findings provide insights into the initial dark chemistry stage of the formation of ice on the interstellar dust grains that will grow into the centimeter-sized pebbles from which planets and possibly life may form. Here's a Hubble image of a white dwarf star named Laud 37, 15 light-years away. Until now, white dwarf mass measurements have been determined by observing them in binary star systems. The motion of 2 co-orbiting stars enables us to use straightforward Newtonian physics to measure their masses. This inset box plots how the dwarf passed in front of a background star in 2019. The wavy blue line traces the dwarf's apparent motion across the sky, as seen from Earth. Though the dwarf is following a straight trajectory, the motion of Earth orbiting the Sun imparts an apparent sinusoidal offset. As the white dwarf passed in front of the background star, the star appears temporarily offset from its actual position on the sky. Given the amount of deflection, Einstein's equations give us the mass of the star. For this white dwarf, it's 56% of our Sun's mass. Here's some history of our coverage of Fomalhaut, a star 25 light-years away. In our How Far Away Is It segment, on nearby stars we covered its protoplanet, Fomalhaut b. In our 2020 review, we covered how this proposed planet had faded away. An analysis of all available archival Hubble data concluded that the planet-sized object never existed in the first place. Now Webb has taken a look at this star and refers to Fomalhaut b as a previously known, collisionally generated dust cloud. That would be a cloud created by a collision, much like our spacecraft collision with Dimorphos created a huge dust cloud. Webb also found that the debris disk around the star is actually multiple debris disks. Planets can clear areas between disks, like our asteroid belt, but as of 2023, no Fomalhaut planet has been identified. The discovery process here is common in science. Early data produces a theory that subsequent, more detailed data proves wrong. The process continues until real knowledge is produced. Here we have NGC 1333, a star-forming nebula 960 light-years away. This view is a composite of light from ultraviolet to near-infrared. Most of the star forming is hidden behind clouds of fine dust. On the right, a bright blue star is illuminating surrounding clouds of gas. At the center, a brighter yellow star illuminates the surrounding gas. On the left, stars surrounded by powerful magnetic fields, direct beams of hot gas deep into the hydrogen all around them. This Webb near-infrared camera image shows the central portion of the star cluster IC 348. Astronomers found 3 brown dwarfs that are less than 8 times the mass of Jupiter. Brown dwarfs are objects that straddle the dividing line between stars and planets. They form like stars, growing dense enough to collapse under their own gravity. But they never become dense and hot enough to begin fusing hydrogen and turn into a star. At the low end of the scale, some brown dwarfs are comparable with giant planets, weighing just a few times the mass of Jupiter. Here they are circled in the main image and shown in the detailed pullouts. The smallest weighs just 3 to 4 times Jupiter. Herbig-Haro objects are bright nebulous regions of gas and dust, formed when material, ejected from a forming protostar, collides with the surrounding interstellar medium. These ejections travel in opposite directions from the star and reach velocities over 700,000 kilometers per hour. That's 435,000 miles per hour. When this fast-moving material collides with slower-moving gas, bow shocks are created, like waves are produced by the bow of a ship plowing through water. This image of HH46 and HH47 was taken by Hubble. The protostar is not visible behind its blanket of dust. Here is the Webb image in near-infrared. At this wavelength, we can clearly see the protostar. It's actually a binary pair of protostars. They are buried deep in a disk of gas and dust that supplies the material for their ever-increasing mass. The disk is not visible, but its shadow can be seen in the 2 dark conical regions surrounding the central stars. The most striking details are the 2-sided lobes that fan out from the actively forming central stars represented in orange. Much of this material has been ejected over thousands of years. The star's more recent ejections appear in a thread-like blue. They run just below the red diagonal diffraction spike at 2 o'clock. They are disconnected at points and end in a remarkable uneven light purple circle in the thickest orange area. Over millions of years, the stars in HH 46 and 47 will form fully, clearing the scene of these beautiful, multi-hued ejections. Featured in this image from Webb is another Herbig-Haro object named HH 211. At roughly 1,000 light-years from Earth, the object is one of the youngest and nearest protostar outflows ever observed. The image showcases a series of bow shocks to the lower left and upper right, as well as the narrow bipolar jet that powers them, in unprecedented detail, with roughly 5 to 10 times higher spatial resolution than any previous images of HH 211. Molecules excited by the turbulent conditions, including molecular hydrogen, carbon monoxide, and silicon monoxide, emit infrared light that Webb can collect to map out the structure of the outflows. Here's a 2023 Webb image of the Crab Nebula. We're zooming into the pulsar at the center. A pulsar is a rapidly rotating neutron star. It produces a vast amount of synchrotron emissions. That's radiation produced from charged particles, circling magnetic field lines, at relativistic speeds. The radiation appears here as light blue smoke-like material throughout the majority of the Crab Nebula's interior. Toward the nebula's edges are cavernous filaments of dust and hot gas. It's made up of fractured material that was ejected at high speeds from the central star. Note the areas where the synchrotron emission seems to be pinched. This indicates that the pulsar is surrounded by a dense layer of gas and dust that slows down ejected matter that passes through it. Here we have a visible light Hubble image of the remnants of a supernova called Cassiopeia A, 11,000 light-years away. We covered it in our How Far Away Is It segment on star clusters and supernova. It has been expanding for just 340 years and spans about 10 light-years. Here's a 2023 image from Webb's near-infrared camera. The most noticeable colors are clumps of bright orange and light pink that make up the inner shell of the supernova remnant. These knots of gas are composed of sulfur, oxygen, argon, and neon from the exploded star itself. Here's a new 2023 mid-infrared image from Webb. The striking colors hold a wealth of scientific information that researchers are just beginning to understand. On the bubble's exterior, particularly at the top and left, we see curtains of material appearing orange and red that are due to emissions from warm dust that's marking where ejected material from the exploded star is colliding into surrounding gas and dust. Interior to this outer shell, there are filaments of bright pink, studded with clumps and knots. A loop, represented in green, extends across the right side of the central cavity. Scientists do not yet understand how its shape and complexity came to be. Here we are zooming in to a Hubble image of Wolf-Rayet 124, 15,000 light-years away. We covered Wolf-Rayet stars in our 2020 review. They are older, massive stars that have completely lost their outer hydrogen and are fusing helium or heavier elements in the core. This is a composite Webb image, combining near-infrared and mid-infrared wavelengths of light. The nebula is 10 light-years across. A history of the star's past can be read in the nebula's structure. Rather than smooth shells, the nebula is being formed by random asymmetric mass ejections. Background stars and background galaxies populate the field of view through the nebula's gas and dust. In 2023, a team of astronomers detected a possible intermediate mass black hole of roughly 800 solar masses at the center of the M4 globular star cluster. In our How Fast Is It video book chapter on black holes, we covered how no intermediate mass black holes have been confirmed to date. But here's one that might be. They examined 12 years' worth of M4 observations from Hubble and resolved pinpoint stars. The suspected object can't be seen, but its mass is calculated by studying the motion of stars caught in its gravitational field. The black hole has an event horizon that is a little more than half the diameter of our moon. This is a simulation of the motions of stars around the suspected black hole. After the zoom into M4, the center of the cluster, where the suspected black hole resides, is highlighted by a red X. The red circle has a radius of just under half a light-year. It delineates the sphere of influence of the intermediate mass black hole. It should be noted that, although an intermediate mass black hole can explain these star movements, other possibilities exist, such as a cluster of stellar mass black holes or neutron stars. So, by the end of 2023, there has still not been a single confirmed IMBH. In the future, the Webb Space Telescope might help resolve this question by improving the star count and velocities near the center. This is a Webb near-infrared image of NGC 346, a dynamic star-forming region that lies within the small Magellanic Cloud, an orbiting dwarf galaxy 200,000 light-years away and 250 light-years across. The region contains numerous molecular clouds packed with dust and hydrogen, the ingredients for forming new stars and planets. Large numbers of young stars are forming in these regions. The many pillars of glowing gas throughout the area are being created by the light from these young stars. The plumes and arcs of gas in this image contain two types of hydrogen, hot in pink and cold in orange. The cold molecular hydrogen areas are dense and dusty. By observing protostars still in the process of forming, researchers can learn if the star formation process in the SMC is different from what we observe in our own Milky Way. Previous infrared studies have focused on protostars heavier than around 5 to 8 times the mass of our Sun. But Webb can probe down to lighter weight protostars, as small as 1/10 the mass of our Sun. The dwarf galaxy UGC 8091 is approximately 8 million light-years from Earth and contains 1 billion stars. It's considered an irregular galaxy because it does not have an orderly spiral or elliptical appearance. Some irregular galaxies may have become tangled by tumultuous internal activity, while others have formed by interactions with neighboring galaxies. The result is a class of galaxies with a diverse array of sizes and shapes, including the diffuse scatter of stars like we see in this galaxy. The red patches are likely interstellar hydrogen molecules that are glowing because they have been excited by the light from hot, energetic stars. Here's an interesting story about unidentified infrared emission bands discovered in the early 1970s. Called UIR bands, they are found in a wide variety of celestial objects, from planetary disks to starburst galaxies, and they have been observed as far back in time as when the universe was a mere 3.3 billion years old. This makes them very important for astronomers to understand. Here's a spectrum of the Iris Nebula taken by Spitzer, showing the UIR bands. Just what could be causing these emissions was a mystery. Astronomer Chris Selgren, while working on her PhD at Caltech, made a discovery that turned out to be the key in unraveling the mystery. She found that sources of the unidentified infrared radiation also emitted continuously in the near-infrared from dust grains heated to 1,000 degrees Kelvin. This temperature was too hot to be from a large number of dust grains, so she hypothesized that while most of the grains were far cooler than this, some would be heated for very short periods of time to 1,000 K by the absorption of a high-energy UV photon. These would then quickly cool to much lower temperatures, creating the unidentified near-infrared emissions. The most likely source for the unidentified infrared radiation had to be a carbon-based dust grain, because they are the only material able to withstand the harsh environments where this radiation is observed. Selgren's discovery led the astrochemists at NASA and a competing group in France to investigate carbon-based soot particles in the laboratory. They found that the emission spectra from the soot produced a good match to the UIR spectrum. The molecules involved are called polycyclic aromatic hydrocarbon molecules, or PAHs for short. They're called aromatic because they actually smell bad in the labs. When a high-energy ultraviolet photon hits the molecule, it is absorbed, creating a characteristic absorption line, heating the molecule to 1000 K, and kicking it into its natural vibration modes. These vibrations accelerate electrons and produce infrared photons ejected in all directions. This drives the molecule's temperature back down to normal. Today, it is understood that this class of molecule is almost certainly responsible for the unidentified infrared emission bands. Research into this kind of radiation continues, with new images from Webb, adding significant additional data. In these 3 Webb mid-infrared images, the polycyclic aromatic hydrocarbons are found mostly within the main dust lanes, in the spiral arms. These images are providing insights into how PAH molecular dust depends on local interstellar medium conditions. This research is important because these particles account for up to 15% of the carbon in galaxies and play a critical role in the formation of stars and planets. They are thought to be the starting material for the earliest life forms. In fact, they may have been vital in the formation of life here on Earth. Here's Webb's near and mid-infrared view of ARP 220, an ultraluminous infrared galaxy with a luminosity of more than 1 trillion suns. It's 250 million light-years away. It is actually the merging of 2 spiral galaxies that began their collision about 700 million years ago, sparking an enormous burst of star formation. The cores of the 2 parent galaxies are 1,200 light-years apart. Near the center, around 200 huge star clusters are packed into a dusty region about 5,000 light-years across. The amount of gas in this tiny region is equal to all of the gas in the entire Milky Way galaxy. The light is so bright that it creates diffraction spikes. Here's a unique way to detect the mass of a black hole. It uses the distortions the black hole creates in background images. Here's an illustration from Durham University. It highlights how the distortions created by using a black hole as a lens can determine the black hole's mass. We start with the distant galaxy, 4.7 billion light-years away. The light from this object passes through the galaxy Abell 1201, 2.1 billion light-years away. The light passes within 3,000 light-years of the supermassive black hole at the center of this lensing galaxy. We can't see the black hole, but we can see the distortions it creates. In this example, the lensing galaxy distorts the distant galaxy image into a wide arc. In addition, some of the light passes near to the central black hole. The black hole acts as a lens and forms a duplicate image of the distant galaxy. To find the mass of this black hole, astronomers, with the help of large computer models, simulated an image that a black hole would create. The output image depends on the mass of the black hole. Mass is an input to the algorithm. Masses too low or too high would not create the image observed, but the correct mass would. The best fit came when a mass of 33 billion suns was input. This mass makes it one of the most massive black holes ever detected. This Hubble Space Telescope archival photo captures a curious linear feature that is so unusual, it was first dismissed as an imaging artifact from Hubble's cameras. But follow-up spectroscopic observations reveal it is a 200,000 light-year long chain of young blue stars. A supermassive black hole lies at the tip of the bridge, at the lower left. The black hole was ejected from the galaxy at the upper right. It compressed the gas in its wake, triggering the development of the young stars. Intergalactic light, also known as intracluster light, or ICL for short, is the light from stars that exist outside of galaxies, in the space between galaxies in a galaxy cluster. These stars are not gravitationally bound to any one particular galaxy in their cluster. They were first detected in the Coma Galaxy Cluster in 1951 by Fritz Zwicky. He reported that one of his most interesting discoveries was observing luminous, faint intergalactic matter in the cluster. Here's a Hubble image. The artificially added blue color is where Hubble data found this intracluster light. The extremely faint glow traces a smooth distribution of light from stars scattered across the cluster. Astronomers are trying to find out how these stars came to be where they are. There are two competing theories. One is that the stars formed inside galaxies and were stripped away by galaxy cluster gas, or by galaxy collisions. The competing theory is that these stars actually formed outside of any galaxy at all. Here's a second galaxy out of the 10 studied for this project. If the first theory is correct, we would expect the percentage of light generated by intergalactic stars to grow over time, as more and more of the stars are produced. But this Hubble survey shows that intergalactic light accounts for around 17% of a cluster's light, no matter how old the cluster is. This suggests that these stars formed at the same time as their galaxy clusters formed. These findings have significant implications for dark matter distribution analysis and the calculations for gravitational lensing, so critical for studies of the early universe. El Gordo is a cluster of hundreds of galaxies that existed when the universe was 6.2 billion years old. It's the most massive cluster known to exist at that time. This image was produced by a combination of Hubble and Webb data. It contains 60 lensed arcs from galaxies billions of light years further away than El Gordo. Here's a sample of the numbering system used to identify each object studied. There are over 180 points of interest. Note the long, pencil-thin line below and left of center. Known as La Flaca, the thin one, it is extremely thin and one of the longest arcs known. One of the most striking features is the bright red arc at the upper right. It's called the fishhook. The light from this galaxy took 10.8 billion years to reach Earth. Its distinctive red color is due to a combination of reddening from dust within the galaxy itself and cosmological redshift due to space expansion. In our gravitational lensing segment of the How Fast Is It video book, we covered how knowledge of the lens properties and critical curves of the foreground cluster enables astronomers to reconstruct the source galaxy's size and shape. Using these techniques, astronomers were able to determine that the background galaxy is disc-shaped and 26,000 light-years in diameter. That's about 1/4 the size of the Milky Way. Another fascinating find in El Gordo is the first individual red supergiant star beyond 1 billion light-years from Earth. Until now, all previous stars discovered at high redshifts have been hot blue stars. Betelgeuse and Antares are the brightest and best-known red supergiants in our Milky Way galaxy. This star is named Quiller. Such stars at high redshift are only detectable using the infrared filters and sensitivity of the Webb telescope. The outer yellow circles mark the positions of two counter images of a source that brackets the position of the critical curve. The white central circle marks Quiller. Here's a Hubble image of Able 2744. It's 4.2 billion light-years away. It's named Pandora's Galaxy Cluster. It acts as a gravitational lens into even more distant galaxies, seen as bluish distorted lines across the cluster. Here's the view from Webb. You'll note that the distorted images of the more distant galaxies are now reddish. That's because this is seen through Webb's near-infrared camera. Zooming out, we see areas that have never been imaged by Hubble. Astronomers estimate that there are around 50,000 sources of near-infrared light in this image. Bright white sources surrounded by a hazy glow are the galaxies of Pandora's cluster, a conglomeration of massive galaxy clusters, coming together to form a megacluster. The concentration of mass is so great that it produces one of the strongest gravitational lenses known. It's the lensed galaxies themselves that are the object of this study. Astronomers used a process called photometry to estimate the distances to the many warped background galaxies. The technique measures light intensity through various filters and compares the results to a database of model galaxies. Results showed that 6 of these 7 galaxies that are close together on the sky are also at the same distance behind Pandora. Later, spectroscopic analysis, which takes a good deal longer to collect, determined conclusively that all 7 were at the same distance, with a redshift of 7.9. This would make them all members of an early galaxy protocluster that formed just 650 million years after the Big Bang. One of the largest programs in Webb's first year of science was the Advanced Deep Extragalactic Survey. The object of the study is to learn how the earliest galaxies assembled themselves and how fast they formed stars. This Webb image shows a portion of an area of the sky known as Good South. Over 45,000 galaxies are visible in this image. Before Webb, there were only a few dozen galaxies observed above a redshift of 8, when the universe was less than 650 million years old. Webb has identified more than 700 candidate galaxies that existed before that. This was far beyond predictions from observations made before Webb's launch. A team named the Cosmic Evolution Early Release Science Survey, CEERS for short, produced this image. It includes over 100,000 galaxies. Spectroscopy has identified 3 of the oldest ones. Here we see that 3 lines appear in the same order for all 3 galaxies. 1 hydrogen line, followed by 2 ionized oxygen lines in each spectrum. The further to the right this pattern falls, the older the light source. CEERS 3 emitted its light 13.2 billion years ago. CEERS 24 and CEERS 23 emitted their light 13.3 billion years ago. On July 1, 2023, the European Space Agency launched a new space telescope named Euclid. Its mission is to explore the composition and evolution of the dark universe. Euclid will explore how the universe has expanded and how structure has formed over cosmic history, revealing more about the role of gravity and the nature of dark energy and dark matter. We'll close our 2023 review with its first 5 images. This image shows 1,000 galaxies belonging to the Perseus cluster, and more than 100,000 additional galaxies further away in the background, each containing up to hundreds of billions of stars. At approximately 1,375 light-years away, in the vast Orion molecular cloud, the Horsehead Nebula is the closest giant star-forming region to Earth. The galaxy IC 342 is nicknamed the Hidden Galaxy because it's difficult to observe, due to the fact that it lies behind the dusty disk of our Milky Way. The dust, gas, and stars obscure our view. NGC 6822 is an irregular dwarf galaxy. It's just 1.6 million light-years from Earth. Here's globular cluster NGC 6397. It's a collection of hundreds of thousands of stars held together by gravity. Located about 7,800 light-years from Earth, it is the second closest globular cluster to us. I expect that the 2024 review will contain a number of Euclid's findings. Here are the links to Hubble and Webb sites, white papers, and other locations where I found the information contained in this 2023 review. these are also the places where you can begin to do your own research. And don't forget, every video has a document on the howfarawayisit.com website containing all the text, links, pictures, and other additional information. Download and translate as needed. In closing, I want to thank Jonathan Onstead for his excellent editing. And I want to thank everyone for all the great comments and questions posted on my videos. I read them all. Keep them coming, and thanks for watching.